Hello, welcome to Fundamentals of Acoustics. Today is the fourth day of this week, and what we will be discussing today is the gas law equation as it concerns the development of one dimensional wave equation. So, the law which we will develop, or the equation which we will develop, it will relate pressure and volume for the gas which is undergoing change as sound is getting propagated in the medium. Now, in reality, there are several processes which can potentially occur. So, as a piece of gas which has pressure, volume, temperature, it undergoes change. There could be, it can undergo change following a variety of processes. Some of these processes are adiabatic process. So, here the governing relation is Pt Vt to the power of gamma is constant, or it could be isothermal. So, here the governing relation is Pt Vt equals constant, or it could be isobaric. So, here the governing relation will be Vt, pressure is constant, is equal to RTT or R temperature, or it could be polytropic expansion. So, here it could be Pt Vt to the power of some constant, n is constant and so on and so forth. So, this gas can follow any one of these processes. So, we have to make a choice as to which process does it follow, and in that context the only way we can make that choice is by having some sense of reality as to how gases or the fluid media is changing its pressure and temperature and volume as sound gets propagated through it. So, based on experience, based on a lot of experimental data, we can say with certainty that when the gas experiences changes in pressure, volume and temperature, it is pretty close to the adiabatic process. And the only reason we are saying that is that this is based on a lot of experimental data and understanding of the physical phenomena, because theoretically I can take either one of those and I can develop the wave equation, but then that final wave equation may or may not be correct. It will be incorrect if one of these assumptions, if the assumptions we make here are incorrect. So, we are selecting the adiabatic process because we know for sure, based on a lot of experimental data, that when sound propagates in air, the gas or the air experiences adiabatic expansion or compression. So, that is based on experimental data and a lot of observation. So, if that is the case, then we say that Pt Vt to the power of gamma is constant, or if I differentiate it, I can write it as partial this total derivative of pressure with respect to time Vt to the power of gamma plus Pt Vt to the power of gamma minus 1 times gamma times partial this total derivative of volume with respect to time is equal to 0, or total derivative of pressure with respect to time is equal to minus Pt over Vt times gamma dVt over dt. Now, what I do is I expand the LHS, and once I do that, I can write it as total derivative of pressure with respect to time is partial of pressure with respect to time plus partial of pressure with respect to x times dx over dt, and that equals minus Pt gamma over Vt dVt over dt. Now, dx over dt is equal to u, because x in this system represents the position of the fluid element, which we saw in while we were developing the momentum equation. So, x represents the position of the fluid element. So, change in x represents change in position of the fluid element. So, dx over dt is velocity of the fluid element. So, I can write it as partial of pressure with respect to time plus partial of pressure with respect to x times u equals minus Pt gamma over Vt dVt over dt. Now, we look at these terms and we realize that pressures, velocities, all of these entities are very small. But before we do that, we will simplify this right side once more time. So, we realize that Pt, which can change with x and time, is equal to P naught plus P x and time. So, del Pt over del x is equal to del P over del x, and del Pt over del t is equal to del P over del t. So, I can write this relation as del P over del t plus del P over del x times u is equal to minus Pt gamma over Vt dVt over dt. Now, we realize that partial of p with respect to time is very large compared to partial of x times u, for the simple reason that this is a product of two small entities, partial of p with respect to x and u, and this is just one small entity. So, if that is the case, then I can simplify this relation as del p over del t equals minus Pt gamma over Vt dVt over dt. Finally, we say that volume, which is the total volume, which can change with respect to x and t, is equal to initial volume of the fluid element plus change in volume, which is tau. Since V naught is constant, so dVt over dt is equal to d tau over dt. So, this relation further gets modified as partial of p with respect to time equals minus Pt gamma over Vt d tau over dt. Then we say that Pt xt is equal to P naught plus P xt, and P is very small compared to P naught. So, in this term Pt, I can approximate Pt as P naught. So, I write this relation finally as partial of incremental pressure with respect to time is equal to minus P naught gamma over V t d tau over dt. So, that is the gas law, and it is based on adiabatic process. If we had assumed that this process was isothermal in nature, then the overall governing equation would have been Pt Vt is equal to constant. And when we compare this relation with this relation, the only difference is this factor of gamma. So, if I remove gamma from here and make it 1, that will be the gas law based on isothermal process. Historically, this relation was first developed by Isaac Newton, and he assumed, because at that time probably we didn't have a lot of experimental data on how sound propagates. So, he assumed that the air, when it expands and contracts due to transmission of sound, it follows the isothermal process. So, the law which he developed, gas law which he developed, was partial of pressure with respect to time equals negative P naught, but he did not take gamma as gamma, but it was 1 divided by V t times d tau over dt. Okay. But once the wave equation got developed using that assumption, it was found that the velocity of sound which it predicted was significantly less than the velocity of sound which was actually measured. So, later Sir Rayleigh made that correction, and he used the assumption of adiabatic process, and once that adiabatic process was used, then the predictions were much better. That concludes our discussion for today, and tomorrow, which is the 5th day of this week, we will continue this discussion, and what we will do in that discussion will be that we will then merge this gas law, momentum law and the continuity law into one single equation and develop the final 1D wave equation. So, thank you, and we will meet once again tomorrow. Bye.